everyone. Welcome to our keynote for today, teaching experimentation on raw data using multiverse analysis by Nathan Tabak. I'm very happy that everyone is here today. Very exciting to be wrapping up our wonderful week of ECOTS. So Nathan is currently the Director of Data Science Programs and an Associate Professor teaching stream in the Department of Statistical Sciences. Before joining the University of Toronto in 2013, he held positions at the Harvard School of Public Health, private consulting, and the pharmaceutical industry, where he worked mainly on clinical research. He is one of the founding members of the Insecurity Insight, an international NGO that uses data to document and analyze violence against aid workers and refugees, and the president-elect of the newly created Data Science and Analytics section of the Statistical Society of Canada. His research interests include data science and statistics pedagogy, communicating data, and the application of computational and data science methods across disciplines. He is currently serving as the special advisor to the Dean of Arts and Science on computational and data science education. Please take it away, Nathan.
Thank you very much, Megan. So it's a pleasure to be here, and thank you very much for inviting me. And it's been an awesome conference so far. So today, what I'm going to be talking about is teaching experimentation on data using multiverse analysis. Okay. So just a quick outline of what I'm going to be talking about, just an introduction about why I think this is important, multiverse analysis, teaching multiverse analysis, available packages to teach and to do multiverse analysis, and then finally ending off with an example and some conclusions. So let me start with how did we go from statistician to data scientist, and I think that also plays a role in why teaching experimentation on raw data is important. Google in the early 2000s, between the mid 1960s and early 2000s, there were various exhortations from lots of people that statistics is only one part of data analysis, and that academic statistics should move closer towards the science of data analysis. Fast forward to the early 2000s, and in the early 2000s, Google was a startup. It's hard to believe that now, and they were trying to figure out how to be profitable. There was a lot of pressure from its backers, VCs, and at the beginning, they used user data to basically just to improve their search engine. In April 2002, the Google data logs team arrived at their offices one morning to find that a peculiar phrase had surged to the top of the search queries, Carol Brady's maiden name. As the logs were passed through the office, people were wondering, why would there be a surge in interest from a character from a 1970s sitcom, The Brady Bunch? But the data could only reflect patterns and not explain them, obviously. A data scientist, Amit Patel, recounted the event to the New York Times, noting that you can't interpret it unless you know what else is going on in the world. So what else was going on? The pattern of queries had 5 separate spikes, each beginning at 48 minutes after the hour. Then they learned that the query pattern occurred during the airing of the popular TV show, Who Wants to Be a Millionaire? And that's the screenshot over there. And the spikes reflected the successive time zones which the show aired, ending in Hawaii. In each of these, the time zones, the show's host posed the question of what is Carol Brady's maiden name? And then in each time zone, the successive searches flooded Google servers. And people at Google, they were basically stunned by the predictive power of search queries. The firm's appreciation of this kind of behavioral surplus crossed a new threshold. And Hal Varian, who had that famous quote that the sexiest job in the next decade will be a statistician, explored this theme of computer-mediated transactions using a computer basically in the middle of every transaction. And other uses included data extraction and analysis, new contractual forms due to better monitoring, and personalization and customization, and continuous experiments. Data extraction and analysis, Varian writes, is what everyone is talking about when they talk about big data. So statisticians with skills that included this kind of iterative exploratory data analysis, computing with data, and statistical prediction is what is I think how we mainly got here from going from statistician to data scientist. And these were the skills that were really valued by Google and Varian at that stage. So the precision of this Carol Brady data was eye-opening. And Sergey Brin said that, it was like trying an electron microscope for the first time. It was like a moment-by-moment barometer. There were other examples of the predictive, power of the searches, related to an earthquake in 2001 near Seattle. The Google searches, the Google servers got flooded with searches related to that. Around September 11th, searches for the World Trade Center and CNN showed up immediately. Over the next few days, Nostradamus, etc. But what was really surprising about the Carol Brady thing is that it was relatively trivial, and yet it went to the top of the surge. So this was kind of a paradox of the Google log. It doesn't capture social phenomena per se, but merely the shadows they cast across the internet. And it reminds me of this quote from Tukey and Wilk. The statistical data analysis is much more appropriately associated with the sciences and with the experimental process in general, because there's a lot of experimentation that went on to try to figure out where this was coming from. So going back to how did we go from statistician to data scientist, I found this quote from a sociologist, Dorschel, and talking about data scientists are hybrids who combine generally conflictive roles as generalists and specialists, technicians and communicators, data exploiters and data ethicists, and they do this explorative work to establish growth for digital capitalism by generating these behavioral patterns that allow for personalization, customization, and optimization practices. So the key idea here, at least for me, is that data scientists explore and discover, which leads to these conflictive roles. Unlike what he goes on to say, what Dorschel goes on to say is as these one-dimensional professionals, such as statisticians and computer scientists. So data experimentation, Tukey referred to specific techniques such as three-way analysis of variance as data analytic hardware. The mystery and art of when and why to use such techniques, he called data analytic software, which he said was very soft indeed. So Brin's analogy to data analysis of the Carol Brady data as an electron microscope could be classified as data analytic software. So if you imagine you were on the data logs team at Google in the early 2000s, how would you know to look at those temporal spikes in search terms and what was happening on a quiz show? I mean, it's just not obvious at all. And this is the type of thing that Tukey had in mind when he talked about data analysis being closer to an experimental science than a branch of mathematics. And so I think one of the most important skills needed for the modern data scientist and statistician is when and why to use techniques on raw data to find meaning and insight. So that takes me here to multiverse analysis. And let me kick off with an example. So this article in Proceedings of the National Academy of Sciences had to do with looking at the names of hurricanes and their gender associated with them. And the title, as you can see, female hurricanes are deadlier than male hurricanes. And what the article concluded was that they used more than six decades of death rates from US hurricanes to show that feminine named hurricanes cause significantly more deaths than do masculine named hurricanes. And they go on to say that this finding indicates an unfortunate and unintended consequence of the gendered naming of hurricanes, with important implications for policymakers, media practitioners, and the general public concerning hurricane communication and preparedness. So how did they do this? So they had coders, 9 independent coders, who were blind to this hypothesis, rate the masculinity and femininity of historical hurricane names on a 2-item scale. And then they were averaged to compute a masculinity-femininity index. Then they ran a series of regressions, negative binomial regressions, and to look at the effect of this masculinity-femininity index on the number of deaths. And then they adjusted for minimum pressure, the amount of damage, and some other features as well. And what I've highlighted here in yellow is, and I've put some terms in brackets here, is that you can imagine that there was no good reason to run a negative binomial regression. The count could have been transformed into using, let's say, a log, add 1, take the absolute value, and then maybe you're looking at a Gaussian, or the count could have been analyzed as a Poisson. The hurricane names could have been the masculinity, femininity could have been treated as a continuous, or it could have just been categorized as male, female. Minimum pressure could have been transformed, etc. Log number of deaths, the outcome could have also been transformed as well. So you can see that there's a whole variety of different options that that could have been done in terms of like the data processing choices and the modeling choices. So what I've done here, if I can get it up, is I've drawn out a sample of what I would call at this stage, a hurricane multiverse. So, so taking the data, looking at, let's just say, for example, damage. It could have been treated as damage or the logarithm of damage, and then just going down the left-hand side of the tree. And then we could have treated the masculinity, femininity index as the continuous variable, or as a categorical variable. And then within that, we could look at log deaths or deaths. And then we could look at a Gaussian or Poisson model, for example. And then what you would end up here is with, 2 times 2 times 2. So 8 different, what I'm going to call universes. So what I have on the right side is output from an R package that that's called Mverse, which literally runs all these analyses for you. And what you see just quickly is that the dots are the coefficient of femininity, and the bars around the vertical bars are the 95% confidence intervals. And you can see that according to the different specifications, that if you go down from the top panel, is so for example, the first specification, NDAM here, if I can get my mouse here. So NDAM, so here it was treated as just untransformed variable, and then in the other one, it was treated as the logarithm of the transformed variable. And then if you go up to the estimate of the coefficient, you can see the different coefficient estimates. And they're colored by whether or not the p-value for the coefficient was less than or equal to 0.5. So going down, you have all these different specifications of these different 8 universes. And this is a very simple example of a multiverse analysis. And then you notice that, really only 2 of these specifications are statistically significant at the 0.05 level, and the rest aren't. This was published in a paper by Simonson et al. And this is what they did, is they basically did a much more sophisticated version of what I just showed you, where in the green part, they have each dot in the top panel depicts the marginal effect estimated at the sample means of a hurricane having a female rather than a male name. And then the dots vertically aligned below with the different specifications. There's a total of 1,728 specifications. And you can see that what's worth noticing is that the original specification here is this one over here, where it's the large black dot. The other smaller black dots are specifications that led to a p-value of less than 0.05. And then the rest of them in blue are not significant. So assuming that all of these specifications are equally plausible, then what can we conclude about the conclusion? And what they concluded again was that death rates from US hurricanes show that feminine named hurricanes cause significantly more deaths than do masculine named hurricanes. I don't think I have to sort of explain that to this audience, but what you would conclude is that it seems that, assuming that all these things are equally plausible, that really that the reported result is dependent on the particular specification of how the data was treated. Okay, so this takes me over to multiverse analysis. So multiverse analysis, as was developed in a paper by Stegan and Gelman around in 2016, and they state that it starts from the observation that data used in analysis aren't just passively recorded in an experiment or an observational study, but they're actively constructed. Transformation of variables, discretization, linear combinations, etc., and creating subsets that might be excluded leads to many possible data sets for analysis. But what typically happens is that researchers often select a single data processing choice and then present this as the only analysis that ever would have been done. So choosing among the various possible data sets is often arbitrary. And a multiverse analysis involves performing the analysis of interest across the whole set of data sets that arise from different reasonable choices. So that's the key thing. It's that it's a reasonable choice. This type of analysis, I think, embodies Tukey's idea that data analysis is this iterative process that requires human judgment at every step. So, how did we, make the decision to log transform it, or, treat male female as a continuous versus a categorical variable? I mean, these are all judgments that require human intervention. Discretizing age, has yielded, for example, interpreter results in many different data sets. That's how we would know to, let's say, even consider taking age as a discrete variable, because we've seen it before. And so this first quote here from Tukey is that, about how to treat data, it doesn't really come from experiments or theory, but rather through analogy between situations which are known to behave similarly. And multiverse analysis, I think, provides a paradigm for iterating through these judgments made by the analyst, and I think would be very helpful in teaching students about the art of data analysis. So in terms of teaching data analysis, how do we teach students about this, this iterative process about, the so-called PPDAC around, problem, what's the problem, what's the plan, how are you going to treat the data, the actual data itself, the analysis, and the conclusions. It seems that multiverse analysis would fit in with between 4 and 5, the analysis and the conclusion, and also, like, other other diagrams out there, and there's many of these. For example, the clean, transform, summarize model diagram that is, for example, in R for data science, might be another way to summarize, let's say, just that 4. But I think, teaching students this whole process is really key, like throughout their degree as definitely as a program learning outcome. And I think what multiverse analysis helps do is I think it makes a lot of these arrows, these kind of circular arrows going back and forth, explicit. So teaching multiverse analysis. So again, raw data can be transformed, which may change the way analysis, results, and conclusions behave. But these transformations, a lot of the time, are reasonable and justifiable. So for example, this year, multiverse analysis was introduced in one of our capstone courses this year, where they read and discussed the Gelman article on the Garden of Forking Paths, and then they actually did a multiverse analysis as part of a class assignment. And so where could it be incorporated into a course? I think, for example, in a course research project involving data analysis, learning objectives related to data analysis concepts such as transformation, interpretation, communication. And then learning objectives related to computing with data. So for example, data wrangling. And this is really one of the reasons that computing is so important in statistics, is to be able to do this kind of iterative data analysis. So what's required to teach multiverse in a course? Well, you need a rich data set, and a data set that has dependent and independent variables that can be transformed, or it's of interest to analyze subsets. So for example, exclude certain parts of the data. Here's a quick discussion of, from the Indian Journal of Psychiatry, should age be treated as a number or just a variable? And I think that there's scope for discussing these types of things in courses on data analysis. And I think that multiverse leads to, this kind of multiverse concept leads to discussing these types of issues. And then, of course, you would need to have integrated computing into the course in order to actually carry out these analyses. So multiverse packages that I'm currently aware of, it doesn't mean that other ones don't exist, but these are the ones that I'm aware of. So there's Multiverse, which was built by Abhinanil Sarma and Matthew Kay at Northwestern. I was involved in that project. Mverse, which we built on top of Multiverse, is a kind of easier to use version of Multiverse, and I'll get into that more in a little bit. In Python, there's a package named Boba. The R packages are available on CRAN, and Boba is available on PyPy. And I think what these packages offer is a computational paradigm for the iterative and subjective parts of data analysis. And let me show you why. So why develop a new package to conduct a multiverse analysis? So I mean, a lot of this stuff can be done, in base R or using the tidyverse. So, so I'm going to start off with a toy example, just so that I hope it's easy for everyone to follow the code. So I'm going to start off with a data set with a data frame with 2 columns, Y and X. And I'm going to, the next thing I'm going to do is I'm going to run a linear regression of Y on X. The next thing I'm going to do is run a linear regression of Y on a transformation of X, which is the logarithm of the absolute value of X plus 1. I'm going to summarize both those models. And then basically create a table of that summary. So this is fine, and this is an example of a multiverse analysis. But the problem is that once you start getting into many, many different specifications, many different models, and many different transformations, the number of possibilities just keeps on growing. Another sort of issue is that, this code is redundant, copy, paste, copy, paste, copy, paste. And I mean, a few times is okay. But, once you get into like 10, 20, it starts becoming very redundant and very error prone. So, ideally, maybe, students would write a function to do this, or they'd use a built-in function. And I think that that's what the next package, Multiverse, tackles. So here again is the same example. And this is the package that was written by Abranil Sarma, a PhD student at Northwestern, Michael Moon, a PhD student at U of T, and Matt Kay, CS prof at Northwestern, and others as well. So the first step is to define a multiverse object. And what I've done here is I've written the double full colon is just to indicate what package the function comes from if you're not familiar with the syntax. Then the next step is to create this environment using the inside function in their package. And what this does is we create branches. So for example, the branch over here has there's no transformation. It's just the outcome on X, and then the other one is the log of absolute value of 1. And then the next step is to run the linear model of Y against the different options for X. And then finally to summarize it. And then the next step is to expand the code, extract the variable that we're interested in. In this case, it's the summaries. And then because of the complicated data structure, it requires this unnesting. And then you end up with output that looks like this. And I think that this is slightly complicated for sure for beginner R users. And probably even intermediate R users. So for example, the dot results column is a list of R environments. And it could be used to extract different things using the $ operator, but I feel like that's very complex. The other option would be that the package offers is to do this in something called a multiverse code chunk. So, so I just took a quick screenshot of it here, but essentially you define the multiverse object outside of in a regular R code chunk, but then the package offers this this way of defining a special code chunk where it's basically where it does all this computations in this environment, and then finally you can run you can execute the multiverse environment in a regular R code chunk, and you end up with the same output. But again, it's I think probably switching from an R code chunk to a multiverse code chunk back to an R code chunk is slightly complicated for especially for beginner users. So here's Mverse, the package that we wrote to be more a little bit more user friendly on top of the multiverse function, and it was written by myself, Michael Moon, 2 students, Howda Lee and Mingwei Chu, and Fanny Chevalier, and Allison Gibbs. So, so the first step is to create a multiverse environment using the data. Define the branches. So here the branches are just X, and then the transformation of X, logarithmic transformation. Then add the branches to the multiverse M. Then add the formula branch. So here we're just going to, the formula is going to be Y on these 2 different options for X. Then add it to the multiverse. And then we've written a wrapper function, a function that does that computes the linear model on all these options. and then a summary function that summarizes that linear model. And then the output is just kind of more what you would expect, but on the left side, columns that indicate which branch you're on and what options they are. So the advantages here, I think, are that it's familiar introductory dplyr verbs, base R syntax, and then it outputs a familiar tibble or data frame as the results summary. So as I said before, it's Mverse is built as an easier to use version of Multiverse. There's wrappers for t-test, LM, linear models, GLM, and then the negative binomial GLM. We also have wrappers for Cox proportional hazards models that we're going to include in the next release. The other advantage is that you don't have to declare a multiverse code chunk or a multiverse environment using the inside function. So now I'm going to move on to an example of that was in the Stegan et al. Paper, where they looked at the effect of fertility on religiosity and political attitude. And this comes from a paper by Durant et al. In 2013, where they classified women into high and low fertility, high being if they were 7 to 14 days within their cycle, and then low if they were at the towards the end of their cycle, based on their cycle day at the time of serve day. And what each participant gave is the start date of their last menstrual period and the previous menstrual period, the expected start date of their next menstrual period, and the typical length of their menstrual cycle. So there's one way to compute the cycle length is to take the start date of their last period minus the start date of the period before last. Then that can be used to compute their next menstrual onset by just adding that to the start date of their last period. And then assuming a 28-day cycle, you could figure out the cycle day from that. And I won't get into all the arithmetic here, but it's fairly straightforward if you stare at it for a little bit. But instead of using a computed cycle length, you could have used reported cycle length or estimated next menstrual onset by the start date of their next cycle that they reported. And then this would give us different cycle days and might lead to different women being classified as high or low fertility. So for example, in a tidyverse analysis, we would prepare the data for analysis here. We could do for example, a mutate statement here to define all these variables. So the computed cycle length over here, the two versions of next menstrual onset, according to whether or not it's a computed cycle length or reported cycle length. And then the two different ways of computing where they are in their cycle. So cycle day 1 and cycle day 2. And then these would lead to two different ways to classify women into high and low fertility. So fertility 1 and fertility 2. And then relationship, which I haven't really talked about, but it's plausible to classify women in relationship if they had indicated that they were coded as a 1 or a 2 or just a 1. So there's two different versions of relationship. And then finally, the dependent variable is just an average of a way that religiosity was measured. And so then the modeling here, again, it's you would maybe run a linear model and then look at the ANOVA table, which is what they did in the paper. And again, you're just copying and pasting code with different variables. So for example, here, if one were to do this just in tidyverse, copying and pasting, you might run the 4 models, and then put it all together in a nice data frame. And there's some data wrangling here, and then plot using ggplot, for example. And then the thing to notice here is that again, that two of the coefficients for the interaction between fertility and relationship turn out to be statistically significant, and two don't. So it depends on the data processing options that one chooses. So for Mverse, I won't run through the whole thing, but again, there's a data prep step, and then the Mverse part, where basically the data processing options would go in this mutate branch part. And again, there'd be two options for fertility and two options for relationship, and then adding them to the multiverse, and then finally using the linear models function in Mverse to run all those regressions in one shot, and then it outputs a nice data frame that's familiar and easy to manipulate. Another function here is something called multiverse tree, where you can see the actual multiverse that you've run. So here I've just printed out part of it, and I haven't cleaned up the labels for these nodes, but it's a ggplot object, so that could easily be cleaned up. And then in a further release, we're going to add parameters so that that it's pretty easy to clean up these labels. And then finally, here's a specification curve where it shows you the different data processing choices that have gone into this, and the coefficient here on top of the fertility and relationship interaction. And what we see here is that the two of the data processing choices. So if you use the cycle day 2 with relationship categorized as just 1, then that ends up with a non-significant interaction coefficient. And then again, basically almost the exact same model, but with cycle recorded as that, then again, it ends up with a non-significant coefficient. But here, all of a sudden, if you change it, change these models, for example, from this one, from the second one to the third one, and you just change a relationship here, the coding here, then all of a sudden you end up with a significant coefficient, etc. So, I mean, you can see that the results aren't quite stable. Oh, sorry, let me go back there. And then again, this is a ggplot object, so that you can, that all of these different labels could be modified. So what have we learned? So there's been major shifts in recommended statistics curriculum over the past decade to include computing with data in the practice of statistics. Modern statistics and data science students should gain experience with the mystery and art of data analysis. Mverse, I think, can be viewed as a computational paradigm for gaining experience with this iterative and subjective part of data analysis. Here I've included the packages, and I encourage you to download them and play with them, and maybe even consider incorporating this type of analysis, even if you don't use the package, into your courses. And I'll leave it at that. Thank you.
Well, thank you, Nathan, for a really great and stimulating talk. I really think it's critical that we think about some of the questions you've been exploring, particularly how we, decide what we teach, particularly as it comes to p-values, the idea that it's not just, all things just get addressed by a single study. And but we do have some questions that have come in. The first one is, you mentioned we need to concern ourselves with all reasonable approaches. Is there any guideline for what's determining reasonable there? Is there any work done on the hierarchy of those reasonable approaches?
That's a great question, and I think that's where really the kind of the art and a bit of the mystery of data analysis comes into play, because what are those reasonable choices, and how do students try to start exploring those reasonable choices? And I think that they really come from looking at different case studies. So I don't think that there is a hierarchy of reasonable choices. So for example, what is the, like, is there a theorem or a principle that goes around whether or not you should take a continuous variable and cut it up into categories? I mean, I don't think that there's anything really out there, but all we know is that sometimes that leads to a much more interpretable result. And of course, there's other implications, but typically that's the main reason for doing it. And so we know that it's worked in other cases. So typically, we might look at it in the current case that we're examining.
Great. Again, I think that kind of question of this garden of forking paths and how we explore it and to kind of acknowledge that there's all kinds of questions that I think our students need to be saying, and that's both our students in statistics and also those who are focused more on kind of the application in the sciences and the like, this aspect of what responsible conduct of research is. I'm going to take my moderator's kind of hat and wonder this kind of question of, could you imagine how you could teach this in a theoretical statistics course, where you might, could you imagine students simulating like you've been done and trying to look at the properties of different things? Because we know there's a lot of methods out there, for example, to pick the right cutoff and then account for the fact that you've done those multiple looks. And I'm just wondering if either you're thinking about or imagining how this might show up in those foundational courses.
Yeah, I mean, I haven't given it much thought in terms of how that might show up in foundational courses, but I like that suggestion that simulation could be used for that. But again, I think for data analysis, I'm really a big fan of going to real data and real examples, and because I think what ends up happening with simulating data, like using R norm or the T distribution or something like that, something symmetric and nicely behaved, is that it lacks context. And I think for this to be really meaningful for students, I think you really need that context. For example, I think for example, the hurricanes, I mean, this is a study published in a major journal. And I think it's really, interesting to see that, just because you read it and just because the analysis looks kosher, maybe it's not after more thorough examination. And and same with the effect of fertility on religiosity and political affiliations. I mean, that article goes back and makes statements about women at this period of their cycle are like more likely, at the time that the study was done, was more likely to vote for Barack Obama versus Mitt Romney. Which is, it's a bit crazy when you look at the different data processing options. Sorry, Nick, you're muted.
My apologies. Sorry, I'm with you there. There's another question, kind of, it was great to kind of think about how statistician, data scientist, where that fits and things. But someone asked, from the perspective of a more traditional statistician and scientist, what about diagnostics? We have information about which models might be more appropriate or not, and shouldn't we use that information? And then what would you actually conclude? So let me leave that question. There's a two-part question.
Yeah. So actually, what's interesting is I've been working on like doing this type of analysis with as a kind of research project with clinicians at a hospital where they want to use where they've been looking at different cutoffs to try to predict who will end up at the ICU. who will end up in the ICU. The other statistician that I've been working with, we were looking at these specification curves that I showed you, and the person said, okay, but which model do I choose? Right? So like at the end of the day, what do I do? Yeah, so I mean, that's, I think, a bit of an open question. I mean, do you average them? Do you take the ones that, do you use this as some kind of like model selection tool, or, is it, do you use like different things with like test and validation sets? It's not really clear actually how you would use this, but I think probably one of the most important things is that you're looking at the stability of the results.
Yeah.
Yeah.
Well, that really is also kind of starting to get at the second part of this question of how do we think about this, both from a kind of scientific conduct research part, which I think is important viewing, but also, what we need to be teaching. The editorial in the American Statistician in 2019 that was putting forward kind of moving beyond P less than 0.05, I think had some challenges for us as a profession of how do we teach the kind of the broader context people need. And so the kind of second part of the question really is, what do you conclude? And what do we want students to kind of take from this? Obviously, we don't want them to be paralyzed with the kind of, lying with statistics, kind of like trust nothing. There's always something. The instructor is just trying to bamboozle me, in various ways. But how do we kind of give them this sense of the broader scientific process, that whole investigative cycle, and not kind of get stuck in this sense of, one can make the data say anything if you torture them long enough.
I mean, I think so. That's why I think that multiverse is kind of a really interesting idea. In that, that the reason that I drew that sample multiverse tree by hand is because I think it's really easy. If you sit down and think about it for a few minutes, you don't need a computer, you don't need anything else. You can just think, well, if I had a continuous variable, what else could I do with it? Well, I could take the logarithm of it. Yep. If I had, I could make it into a discrete variable, etc. And I don't think you need that many advanced concepts to write those options down on a piece of paper. And so for me, if a student left a course, understanding that those are all different possibilities, and that and in some sense they're arbitrary, and really you're just looking at a model that best describes the data that you have, but you shouldn't believe the model. That would be a real win for me.
Well, again, this really, I think, lays out some of those questions about the need for protocols, kind of analysis plans that we've kind of developed in various ways, and to be as transparent as possible about the array of things that are provided there. There's a related question. Is there any aspect of multiverse analysis, even stopping well short of doing the analysis itself, that could be naturally introduced in an elementary statistics course? Potentially even with less technology? Could you imagine ways of making, identifying what the question writer writes, multiverse ready habits of mind, that people could start to think about some of these broader questions?
Yeah, I think that, even things like looking at, you could even have a discussion about age or gender. I think those naturally lead to different multiverses. Do you treat gender as male, female? Do you treat it as 3 categories or more? And then for example, age. Do you look at age as a continuous variable? Do you look at it as a group, etc.? So I think even basic questions like that, and then what are the implications of that? And I think there's probably questions that are much more that relate to societal type questions. That probably veer into the social sciences, and then there's questions that lead into the analysis, and basically the interaction of those two. What do those types of conclusions mean for how you treat the data? In a book called Data Feminism, they talk about this idea that raw data is an oxymoron, and that the data to some extent is always kind of cooked before the analysis. And I think that what Multiverse brings out, this idea, is that it's really you're kind of getting to peek inside the kitchen.
Yeah, no, I think that's a really valuable insight, because I think we've often historically had this kind of sense that it's all cut and dried. There are yes, no answers. There are other kind of parts and pieces that, it just there's one true path there. And I think the reality is much more interesting and much more complicated.
Yeah.
There's a related question. Would you consider choice of p-value threshold to be part of the multiverse analysis? Is that the kind of things where people might be thinking there might be a different kind of cutoff for perhaps interactions or other types of things?
Yeah, I think that this would be a good place to look at different p-value cutoffs and looking at different specification curves. And because if you choose a different cutoff, you're going to get a different specification curve. And that could also kind of, I think that's a great idea. Like it could kind of help, illustrate that, again, the arbitrariness of picking an alpha with a 0.05, 0.04, or 0.03.
Mm-hmm. Great.
Yeah.
So there's a question about, are you concerned about overloading students? For example, having too many variables and universes so that the table of results or the kind of the map of them becomes almost impossible to parse. And I certainly like that idea that you have introduced so clearly, with starting small with a little bit of tree with the 2x2x2 to give people a sense of the different parts and pieces going on there. Because I think it's going to be important for them to kind of get a handle on the different combinations. But any kind of sense about overloading students?
I mean, again, I think it would have to be scaffolded. But I think it leads nice. I mean, it depends obviously what students are doing in the course, but I think if it's in a course where they're introduced to multivariate thinking, I think this really almost extends that type of thinking in a very broad way. So no, I'm not too concerned.
Okay.
Yeah.
Do you have a sense amongst your biomedical collaborators, particularly those who teach, the next generation of biomedical researchers, how they feel about this? I know there's been a lot of work. It's taken considerable time and effort to standardize the reporting of clinical trials to get to the point where, the consort statement, I think, is well enunciated. It took me longer than any of us hoped. There's generally through clinicaltrials.gov or the equivalent in Canada and elsewhere, kind of good protocols put forward. But, do you have a sense of how they see this fitting into the biomedical curriculum at the graduate level?
Yeah, I don't think that that they see this as right now as a feasible option. I mean, I think, like even just thinking about clinical trials, I mean, what would you write in the analysis plan? I mean, you'd have to write something like, all feasible options, and I'm going to generate a specification curve, and then back to the question, well, what's the answer? And I think that would just be too ambiguous for many. But I think that actually, I don't think it's unreasonable to maybe look at something like a specification curve as part of a clinical trial plan to see how stable the results actually are, provided that everybody could agree on what the plausible specifications are.
Great. Well, Nathan, I just wanted to thank you for a really excellent presentation, very thought-provoking, that really, I think, ties into these questions of what are we teaching, particularly as it comes to inference and the entire cycle, PPDAC, or that entire investigative process, because I think it's critical for us to be thinking about that and not get ourselves, into these little arguments about, what that particular single p-value does or does not say about the bigger questions that statistics and data science are being used to answer. I want to say thank you for this keynote, and I just want to encourage people to take the well-deserved gap they have now between now and the 1:15 p.m. Eastern Time breakout sessions. We have a fabulous set of posters starting at 2:40 p.m. and then our closing session, which I know you don't want to miss. So thank you, everybody, and have a great rest of ECOTS.
Thank you, everybody.